So today we are going to discuss about the recapitulation of the topic dielectric properties of matter or dielectric properties of materials. Uh, we have firstly indicated that what is dielectric polarization and what is the dielectric material. Dielectrics are non-conducting substances, as we all know. They're the insulating materials and are bad conductors of electrical current. And dielectric materials can hold an electrostatic charge while dissipating minimal energy in the form of heat. So examples of good dielectrics are mica, plastics, glass, porcelain, and various metal oxides. So you must remember that even dry air is also an example of dielectric. So there are various classification of dielectrics, uh, such as polar molecules, where polar molecules are those type of dielectric where the possibilities of the positive and the negative molecules coincide with each other are null or zero, and this is because they all are asymmetric in shape, such as example are H2O, carbon dioxide, nitrogen dioxide, etc. When the electrical field is not present, it causes the electrical dipole moment of those molecules in a random direction. This is why the average dipole moment is zero. If the external electric field is present, the molecule assemble in the same direction as the electrical field. And in case of non-polar molecule, unlike polar molecules, the center of positive charge and the negative coincide, it is not zero. The molecule has no permanent or intrinsic dipole moments, such a case is observed in either oxygen, nitrogen, hydrogen, etc. So a matter of induced dipole moment also comes into play when we apply the external electric field in a nonpolar molecule. All the protons travel towards the direction of the electric field and the electrons in opposite direction. So due to the presence of the electrical field, this process continues unless the internal forces balance them. So due to this, there is a creation of new centers of charge. They're polarized and we call them as the induced electric dipole. So the dipole moment is the induced electric dipole moment, right? So we are going to discuss the as you uh, place a dielectric material in the electric field, there is two capacitor placed in between. The dielectrics are sandwiched, so the bound charges are attached to the capacitor plates where the electrode connection are being done, and the free charges are these blue and red charges, which is mobile, rather than the brown charges, which is less mobile or uh, are attached to the capacitor plates. The most important thing we are going to discuss is the interfacial polarization. What is interfacial polarization? As we all know that the interfacial or the space charge polarization occurs when the accumulation in the as discussed in the figure, when the accumulation of the charge at an interface between two materials, in between two materials or in compound dielectrics, this kind of effect are predominant. And so uh, two materials or between two regions where within a material because of the external field. These can occur when there is a compound dielectric, as I mentioned, or when there are two electrodes connected to a dielectric material. So this type of electric polarization is different from orientational or ionic polarization, because instead of affecting bound positive or negative charges, that is ionic and covalent, um, bonded structures, interfacial polarization also affects free charges as well. So as a result, interfacial polarization is usually observed in amorphous or crystalline solids, where the figure shows an example of how free charges can accumulate in a field causing interfacial polarization. The electric field will cause a charge imbalance because of the dielectric material's insulating properties. However, the mobile charges in the dielectric will migrate over maintain the charge neutrality. This even causes the interfacial polarization. The figure mentions how free positive charges inside the dielectric material migrate towards the negative charge buildup on the right caused by the external electric field. So the equation to show the space charge polarizability constant is alpha c is equals to alpha minus alpha infinity minus alpha naught, where alpha c is the space charge polarization, alpha infinity and alpha naught refer to the total electronic and the orientational polarizations respectively. So it is important to note that because the charges are free charges, defects such as grain boundaries or other interfaces can serve as a medium for interfacial polarizability to form. So from the equation of space charge polarization, it is then determined that the total amount of dielectric polarization in a material is the sum of the electronic, the orientational and the interfacial polarizabilities. So this is a very important expression. So moving to the next slides regarding the dipole orientations in solids, where we all know that we expect molecules in gases or rather in liquids to be fairly free to rotate, and the permanent dipole moments may be expected to make their full orientational contributions to the polarizability. Uh, Apart from that, in molecular solids, the ability of a molecule to rotate depends very much on its shape, the strength of the interaction between the dipole with the environment. So the closer the approach to sphericity, the lower the dipole moment and more easily the molecule will rotate. So thus, solid methane CH4, which is the asymmetrical nonpolar molecule, rotates quite freely in the solid state. And the molecule in solid hydrogen also rotates so freely that the Raman lines of gaseous hydrogen are found at nearly the same frequencies at the solid states. So in less symmetrical molecules such as HCl or H2O, at high temperatures, there appear to be several stable orientations for each molecule in the solid, and a molecule will change direction from the one stable orientation to another in a time which is called the relaxation time. Now, the important feature of relaxation time comes when we discuss the dielectric constant of solid hydrogen sulfide versus temperature. The principal feature of this curve is the sharp increase of the dielectric constant as the temperature is lowered. This is as shown in the figure, but the sudden drop below 105 degree Kelvin, which is thought to mark the transition in an ordered state in which the directions of the hydrogen sulfide molecules are frozen. So in a regular array, those nature has not yet been determined. The behavior of the dielectric constant above the transition temperature is of the dielectric constant above the transition temperature is a suggestive of free rotation, but we can show that a similar variation with temperature arises even when there are only a discrete number of allowed orientations for each dipole. Suppose, for example, that a dipole of moment P has two allowed directions. One is parallel to the electric field and one is anti-parallel to the applied electric field E. So we emphasize that the restriction in orientation is imagined to follow from steric or geometrical hindrances in the solid and not from quantization. Magnetic moments are quantized through their association with angular momenta. Electric moments in molecules are not thus associated. So the ratio of the occupation numbers of the two sides will be using the Boltzmann distribution functions like Na over Nb is equals to exponential 2 E times P over Kt. So that the fractional axis oriented parallel to the field is writing x equals to EP over KT, and Na simple algebra brings Na minus Nb over Na plus Nb is equals to e to the power x minus e to the power minus x over e to the power x plus e to the power minus x, which turns out to be tan hyperbolic x. And as the limit x Ep over Kt far lesser than 1 in the limit where temperature is high enough and field is sufficiently low, this tan hyperbolic x becomes only the approximation x. So provided that the x is far smaller than 1. So if there are n molecules per unit volume, the polarization will be in this approximation. The capital P is equals to the number of molecules per unit volume times the dipole moment times x, which turns out to be n p square E over kt, which is very much similar to the Langevin function which we derived the last classes, where p turns out to be np square e over 3 kt. So this 1 upon t dependence is there, which is in agreement with the Langevin function or the established theories. So apart from the numerical factor, which is identical with the result from the Langevin function derived for freely rotating dipoles. So quickly we will move on to the dielectric relaxation and dielectric losses. So the principal part of the difference between the low frequency dielectric constant and the high frequency dielectric constant as measured by the square of the optical refractive indexes may be attributed to the damping out or the relaxation of the orientational contribution to the dielectric constant. So we introduce the concept of relaxation time as the time interval characterizing the restoration of a disturbed system to its equilibrium configuration. The relaxation frequency is defined as the reciprocal of the this one relaxation time. So in inhomogeneous dielectrics, the Maxwell Wagner interfacial polarization mechanism, which leads to another type of relaxation which we shall not go into here. The orientational relaxation frequencies vary over a wide range and may be strongly dependent on the temperature. In water at room temperature, relaxation occurs at about 3 into 10 to the power 10 CPS, corresponding to the wavelength for electromagnetic radiation of 1 centimeter. So in ice at minus 20 degrees centigrade, the relaxation frequency is of the order of 1 kc. So uh, mm, uh, the simplistic approach to understand the why this relaxation occurs, say this is the real part of the dielectric constant over the frequency. As the AC frequency increases, the in the megahertz or the higher kilohertz regions, the molecules are not get enough time to um, orient themselves with the frequency of the highest AC fields. That's why the molecules get relaxed, and therefore this Debye relaxation occurs. So in this graph, as you show that the real part looks like this relaxation process, and the imaginary part also gets this hump type of behavior at this relaxation time. So most energy is lost at 1 over time. See the frequency range. This is the gigahertz, so this is the mid megahertz region, as I mentioned. So this is the typical Debye equation, which I plotted in the next year slides, where the Debye relaxation time. So Debye has given a discussion on dielectric relaxation in polar liquids and in solutions of polar molecules. So the central result is the orientational part of the polarizability depends on frequency as alpha equals to alpha naught over 1 plus I omega tau, where tau is the relaxation time and alpha naught is the static orientational polarizability. So Debye has suggested further that this in liquids, the relaxation time is related to the viscosity eta by relationship which where tau is proportional to eta and disproportional to t. So moving from the other part, this is the typical behavior of the Debye equation. See the dependence of the real and imaginary part of the dielectric constant over log of frequency. So this type of relaxation occurs in most of the materials, dielectric materials. Where in this curve we have showed the same behavior, the same relaxation behavior over epsilon prime and epsilon double prime curves. So the relaxation times in solids are usually much longer than in liquids. So this behavior is somewhat parallel to the behavior of diffusion rates in liquids or solids. Uh, Someone has related the observed dielectric losses in alkali halide crystals to the presence of lattice defects in the crystals where considerable success. So moving on to the complex dielectric constants and the loss angle, we have in the presence of relaxation effects, the dielectric constant may conveniently uh, be written as the complex quantity as epsilon star equals to epsilon prime plus j epsilon double prime, or epsilon can be simply written as epsilon 1 minus I epsilon 2, where the dielectric constant is taking the local field as equal to the applied field. So if the functional form is looks like 1 plus 4 pi times alpha naught n divided by 1 plus I omega tau, it turns out from this equation that the real part of dielectric constant is 1 plus 4 pi alpha 0 n over 1 plus omega square tau square, and epsilon 2 is simply 4 pi alpha naught omega tau n over 1 plus omega square by tau square, where this is the real and imaginary part of dielectric permittivity respectively. The variation of epsilon 1 and epsilon 2 with frequency is shown in the figure, where this is the static part of real part of dielectric constant over frequency. This is at tending to at frequency infinity. This is the uh, real part of dielectric constant at infinity. What the Debye equation says. So this is the loss factor tangent. I am discussing the dielectric loss tangent a bit later. Then the conductivity follows the opposite behavior of the real part of dielectric constant. As frequency increases, this also increases. So the most important feature is that the relaxation phenomena is you have to consider what happens if the driving force, the electrical field in our case, is suddenly switched off after it has been constant for a sufficiently long time so that the equilibrium distribution of dipoles could be obtained. So this is the easiest equation where the power dissipation per unit volume P is given by JPE, where JP is the component of the current density which is in phase with the electrical field. So we have from Maxwell's equation, this J is equals to sigma E plus 1 upon 4 pi delta D delta T, where D is the displacement current. And finally it becomes sigma plus I omega epsilon over 4 pi E. So for which my sigma equals to 0 and epsilon equals to epsilon 1 minus I epsilon 2 becomes j equals to this functional form. So that the power dissipation is finally E square over 4 pi omega epsilon 2 or epsilon 1 E square upon 4 pi omega tan delta. So where loss angle or the power factor is defined as the tan delta is equals to imaginary part of dielectric permittivity over the real part of dielectric permittivity, as we all discussed in the class 2 level. where this real axis is the epsa r prime and the imaginary axis is epsa double prime. Therefore, eventually the angle between the real part and uh, the complex part and the real part are tan, and delta is denoted by the real part of permittivity over the imaginary part of permittivity over the real part. So finally tan delta is equals to d, which is the reciprocal of the quality factor or Q factor of the system, which is defined as the quality factor is defined as the maximum stored energy over the average energy loss per radian. So, which is the dielectric case reduces to simply Q is equals to 1 upon tan delta. That's why tan delta is equals to 1 upon Q, and finally, these types of behavior are being observed. So these are the typical dielectric losses and the dielectric behavior, as we just mentioning that, as we expect that the dipoles will randomize, that is their dipole moment or the polarization will go to zero. However, that cannot happen instantaneously. A specific dipole will have a certain orientation at the same time and field will be switched off, right? So it will change that orientation only by some interaction with the other dipoles or in a solid with phonons. In other words, upon collisions on other violent encounters, it will take a characteristic time, roughly the time between collisions between the dipole moments will have disappeared. That's why, since we are discussing statistical events, in that case, the individual characteristic time for a given dipole will be small for some and large for others. But there will be an average value, which we will call the relaxation time tau of the system, as we discussed in the earlier slides. Yeah, this type of behaviors, the relaxation time tau of the system, we thus expect a smooth change over from the polarization with field to zero within the relaxation time tau, or the behavior as given below. So this is the expected tau. uh, these are the uh, behavior of the transients, I would say, and particularly the complex number functions are comes into play, where these frequency dependent effects or the AC conductivity effects becomes predominant. So the real and the imaginary part of the complex dielectric constant contain different terms depending upon the uh, behavior or the orientational polarizability, and all optical properties and essentially also the conductivity of non-perfect dielectrics. So before we proceed to the dielectric function, which is what we really want to obtain, we have to make thing a little bit more complicated in the other ways, where this type of Debye equation, as I observed in this case, okay. So the reason the frequency dependence of the orientational polarization is so called the Debye equations. So uh, epsi infinity for the high frequency limit, and the complex function epsa omega is the dielectric function. In the equation, it is given in a closed form for the dipole relaxation mechanism. So we write the complex function as a sum of a real part and the complex, and finally the epsa prime at omega equals to 0 is denoted as static dielectric constant epsa s, and epsa prime for omega tending to infinity is designated as epsa infinity. So from the working of the complex notation of the sine cosine functions, this epsa prime are the real part, and which is in phase with the driving force. Epsa double prime at the imaginary part gives the amplitude of the response, and that is phase shifted by 90 degree. So relatively simple curves, actually they always look like a graph shown below. The three numbers that define a particular material, that is epsa s. One is epsa s, epsa infinity, and tau is equals to 2 pi upon omega naught. Only change the numbers on the scales. So what the dielectric function for orientational polarization looks like for real systems can be tried, and epsilon infinity, that must be 1 for some value determined by some other mechanism, as also exists. So epsilon s, we can get the polarization mechanism for the materials being considered, and if we know the dipole moments of the materials and their density, the Langevin function gives the static polarization and thus epsilon s. So we will now not, however, obtain tau from the theory of the polarization considered so far. So here we have to know about more about the system for liquids. That is the mean time before two dipoles collide and lose all their memory about their previous orientations. So it is difficult to say that the typical relaxation times are about 10 to the power minus 11 second, which corresponds to frequencies in the gigahertz regime, that is the centimeter waves. And we must therefore expect the typical materials exhibiting orientational polarization, that is water, will show more peculiar behavior in the microwave range of the electromagnetic spectrum. So this is all about dielectric relaxation and dielectric behavior of materials. And finally, it is also clear that tau may vary from quite a bit depending on the material and the temperature. If heavy atoms are involved, then tau tends to be larger and vice versa. So if movement speed up because of temperature, tau eventually will get smaller. So we have come to the final end of this chapter, which is dielectric laws, the absorption of electrical energy by the dielectric material that is subjected to an alternating electric field is termed as dielectric loss. And basically, dielectric loss quantifies a dielectric material's inherent dissipation of electromagnetic energy, that is heat. So it can be uh, termed as either the loss tangent delta or corresponding to the loss tangent tan delta. Uh, So loss tangent is defined as the ratio of the lossy reaction to the electrical field E in the Carl equation of the lossless reaction. That is for dielectrics with small loss, this angle is far lesser than 1, and tan delta becomes delta. And these are the frequency versus the uh, dielectric constant effects for the different regimes, where my small range of frequency, this interfacial and space charge polarization becomes predominant, and sufficiently when it stabilizes, the orientational dipolar polarization comes into play in the radio frequency range. And finally, at the far end infrared region, the ionic contribution of the polarizability comes, and at the ultraviolet light or UV or ultraviolet light region, the electronic polarizability comes. So finally, this epsilon prime is equals to 1. This is the typical behavior of the where in which frequency regime what kind of polarization becomes predominant. This is a very important graph in studying the dipole relaxations and losses. This is the loss tangent behaviors. To extent to which this material is polarized is also frequency dependent, and alpha is frequency dependent. This is the typical some few materials where tan delta are being listed, and particularly in capacitor industries, you have to have a material which possesses a high dielectric constant, real part of dielectric constant, as well as a very low dielectric loss to have a viability in the capacitor or microcapacitor industries in MEMS now. So uh, this is all about dielectric loss tangents. Uh, Nevertheless, these loss tangents have an important role in characterizing the uh, typical behaviors of polymers, liquid crystals, and ceramic materials as well. So simply dielectric constant and dielectric tangent are both numerical values using which we can define permittivity of the dielectric material. The permittivity of a dielectric material is denoted by epsilon prime, and tan delta being called the loss angle. Tan delta is also called the dielectric loss tangent.